Welcome friends to my YouTube channel. Uh, Now in yesterday's lecture I have completed the conservation theorem in classical mechanics. Okay, Mm, that I have finished. So from today's lecture I shall going to discuss the chapter number 4, that is rigid body dynamics. Okay, that is the new chapter, that is rigid body dynamics. Okay, that is the rigid body dynamics. Now we all know that a rigid body consists of so many number of small particles. Okay, a rigid body obviously consists of large number of small particles. Okay, so suppose this is a rigid body and this is the axis of rotation. Okay, that is, if you give it a name, that is, if we assume the axis is AB and the rigid body is rotating with an angular velocity omega with respect to the axis AB. Okay, you can imagine it. So just take a particle, say at a distance r1 you take a particle m1, say at a distance r2 you take a particle m2, say at a distance r3 you take a particle of mass m3. So in this way the rigid body is made up of large number of small particles which are located at different distances from the axis. Okay, so since the angular velocity of the rigid body is omega, so all the particles will rotate about the axis with same angular velocity. Okay, so all particles will rotate about AB with same angular velocity omega. Okay, so all the particles will rotate about the axis AB with same angular velocity omega. Okay, so what will be the moment of inertia of the particle of mass m about AB? First, okay, so moment of inertia of the particle of mass m1, moment of inertia of the particle of mass m1 at a distance r1. This is what, that is simply we can write m1 r1. Sorry, I made a mistake. That is not moment of inertia. That is, at first we are trying to find out the what will be the rotational kinetic energy. Okay, so rotational kinetic energy of m1 about AB, what is this? That is simply half mass m1 and v equals to omega r, that means omega square r1 square. So this is the rotational kinetic energy of the particle of mass m1 about AB. Now similarly, if you call it say E1, okay, now what will be the rotational kinetic energy of the particle of mass m2? So if you call E2, it will be simply half m2 omega square r2 square. Okay, half m2 omega square r2 square. Now what will be the rotational kinetic energy of the particle of mass m3, if you call it e3, this is simply half m3 omega square r3 square. Okay, so this is the rotational kinetic energy of all particles, so from which we can easily determine what will be the rotational kinetic energy of the entire rigid body about the axis of rotation. Okay, so the rotational kinetic energy of the entire rigid body about the axis of rotation. Okay, rotational kinetic energy of the entire rigid body about the axis of rotation, simply e1 plus e2 plus e3 dot dot dot, simply half, we can take omega square common, so it will be m1 r1 square plus m2 r2 square plus m3 r3 square. So we can simply write this term as sum over of I mi ri square, say I equal to 1 to n, and this is known as the moment of inertia of the entire rigid body about the axis of rotation. Okay, this is known as the moment of inertia of the entire rigid body about the axis of rotation. Okay, so this is the concept of moment of inertia in rotational motion. Okay, now let us find out the angular momentum, okay, about the axis of rotation. So what will be the angular momentum of the object of mass, particle of mass m, that is simply m1 mvr, that is mr1 square omega. Okay, what will be the angular momentum of the particle of mass m2, that is m2 r2 square omega. Okay, now what will be the angular momentum of the particle of mass m3, that is simply m3 r3 square omega. Now what will be the total angular momentum of the rigid body about the axis of rotation? Similarly you can add these terms. Okay, so similarly if you take common omega, so it will become m1 r1 square m2 r2 square m3 r3 square plus dot dot dot, or this is simply sum over of I mi ri square. So this is simply L equals to I omega. So this is the relation between angular momentum and moment of inertia, that is L equals to I omega. Okay, so L equals to I omega. Now what we have found till now. Now you give it this linear and this is rotational. Okay, first you see that in linear motion we can write linear momentum, this is equals to mass into velocity. So corresponding rotational motion, p is replaced by L and m is replaced by I and v is replaced by omega. Fine. In linear motion you can write the kinetic energy as half mv square, or here you replace the rotational kinetic energy by half I omega square. Okay, so what similarity we are see here, what similarity we observe here, that is this: I plays the same role as played by m. Similarly, here I played the same role as played by kinetic energy in linear motion. Okay, that is the role that the moment of inertia plays in rotational motion is exactly same that mass plays in linear motion. So this is the most important physical significance of moment of inertia. Okay, that is, it plays the same role in rotational motion as played by mass in linear motion. Okay, so this is the most important physical significance of moment of inertia. Okay, so I plays the same role in rotational motion as played by M in translational motion. Okay, similarly you can write also, that is, in linear motion force is mass into acceleration. In rotational motion, tau, this is equals to what? I alpha. Alpha is the angular acceleration. Okay, so similarly you can find this. Okay, now I shall going to discuss how this relation comes. Okay, so till now we have discussed about the concept of moment of inertia and its physical significance. Okay, so our next task is to find out the this relation tau, this is equals to I alpha. How? This is simple. We write L, this is equals to I omega, that we all know. So just differentiate this expression dl dt. This is constant I and this is d omega dt. So what is tau? Rate of change of angular momentum means torque. This is I, and rate of change of angular velocity means angular acceleration. Okay, so this is how this relation comes. Okay, and you see, that is, if you take alpha is 1, then the moment of inertia is numerically equal to the torque. Okay, the moment of inertia is exactly equal to the numerical value of torque if you take unit angular acceleration. Okay, so for unit angular acceleration, I and tau becomes same. Okay, so in today's lecture, I discuss about the concept of moment of inertia and its comparison with mass in corresponding linear motion. Okay, and we also prove this relation, that is tau equals to I alpha, how this relation comes. Okay, and here we see that for unit angular acceleration, I is almost equal to tau. Okay, so this is the introduction of moment of inertia. Now in our next class, I shall going to discuss few another issues related to moment of inertia. Okay, so video link will be given in the description box, and if you have any query, then just write it in comment section. And if you don't subscribe my channel, then kindly subscribe it to get latest videos. Okay, thank you.